So we'll pick up where we left off. We had reached this point where we're ready to integrate this guy. I'm integrating with respect to volume R over V. Well, how do I know? I need to know how R changes as a function of the volume, of the specific volume. So think about that. How does this ideal gas constant change as a function of the specific volume? And my answer is in the question there. You've already picked up. How does this constant vary with respect to the volume? It's constant, so it doesn't vary. So it comes out of the integral. Now I'm just integrating dv over v. I'm integrating it's r times the integral of dv over v. Well, if you remember the integral of dx over x, that's just natural log, right? So I'm going to do this over to the side. I'm going to do this in the margins, right? So if I'm integrating dx over x, this integral, and this is from x1 to x2, let's say, well, this becomes natural log of x from x1 to x2. All right. And so I've got the natural log of x from x1 to x2. And so this becomes the natural log of x2 minus the natural log of x1. If you remember some basic logarithmic algebra, and if you don't, we'll just go to Khan Academy or you search some YouTube. You'll find a real simple way you can brush up on your logarithmic algebra. If I'm taking the same base log, in this case natural log, of two different things. I'm taking the difference of these two different natural logs. Well, that's the same as the natural log of their ratio. All right, the negative one goes in the denominator. So if I apply the same logic to, I'm integrating dv over v, well, this becomes the natural log of v from v2 to v1, or from v1 to v2, sorry. So it just becomes the natural log of, so I'm just going to write it out, r times the natural log of the ratio of specific volume 2 to specific volume 1. Okay. So what's next then? Well, I can apply pretty much the same logic I've just done here to go from here to here. I can apply almost the exact same logic for the specific heat dt over t. In fact, that's what I'm going to do. Remember, we've talked multiple times. We all This is my third page, and I've got one prior to this. This is like page 4 or something. Okay. We've discussed multiple times that the specific heat for an ideal gas changes as temperature changes, but not a huge amount. So if I take the specific heat at the average temperature, not just room temperature, not just one temperature or the other, the average temperature, then I can assume the specific heat is reasonably constant at that temperature. And the specific heat now comes out of the integral, and I'm just integrating dt over t from t1 to t2. Well, we can use the same logic we just applied here. This becomes now the natural log of t2 to t1, but then I've got to add this term here. This is plus r ln v2 over v1. Now, the rookie mistake is to assume these are speeds or total volumes. These are not. These are specific volumes. Again, why do we do derivations? Well, because you need to know how the tool works in order to use it. This is specific volume. It's from the ideal gas law. So that's how that got there. That's what those V's represent. These are specific volumes, the ratio of specific volumes from state 1 to state 2. Make sure, and we talked about this early on, make sure you know which V you're using. Similarly, we could go through the same derivation. Remember, we had this other term up here, right? What we just derived is from this expression for ideal gases. Remember, there's this one that uses dH and V dP over T. So I can employ the same substitution here. Substitute this in, C sub P dt here, R over P there, and apply the same logic that we just went through. I'm not going to do that with you. We could. And I could tell you, well, delta S is also equal to the integral from T1 to T2 C sub P dt over T. And this one has minus R ln ratio of pressures P2 to P1. Again, that comes from this version of the equation. And this is a hard equal to sign here. We could do the same approximation we just did here to go from here to here. We can also apply that approximation here and say, well, you could take C sub P at the average temperature times the natural log of the ratio of temperatures and still minus this R ln, sorry to go on the margin, P2 over P1. So what you have now is for ideal gases, you have now another way that I can approximate the change in entropy, the left-hand side of the equation. Right? Recall that the second law for a process from state 1 to 2 says that the total entropy change, big S2 minus big S1, or mass times little delta S, these guys, is going to equal the integral of all of the heat divided by temperature plus the amount of entropy being generated. So what I'm saying is, depending on, well, if it's an ideal gas, I can use either this or this as a good approximation for this term. Multiply by the mass, that'll tell me something about the heat transfer per temperature and the entropy being generated. So anyway, what this does is this gives us a tool that I can use to approximate the left-hand side of the second law equation for an ideal gas. That's only specifically for an ideal gas. Now, don't do this with water and R134 because in general, those don't, in the ranges we're dealing with, those normally don't behave like an ideal gas force. Sorry, I'm reaching for notes over here, and you can see I'm casting some shadows. I want to make sure I derive correctly for solids and liquids. This is another situation where I can go ahead and describe how, going back to the original Gibbs equation, for solids and liquids, I can describe how the internal energy changes with respect to temperature, and I can also describe how pressure and temperature cause changes in specific volume. They essentially don't, right? So what essentially happens is for solids and liquids, we say, well, ds is equal to du over t plus, and that was p dv over t. And essentially what happens is dv is essentially zero. The change in volume for solids and liquids is almost negligible. The temperature is really what drives this change. So what happens is we do the same thing we did up here. We integrate with respect to, we integrate from state 1 to state 2. So this now becomes delta S. These are little s's, delta little s. We can approximate as your textbook, the Changle and Bowles textbook, uses C sub P at the average temperature to describe delta U. So it'd be C sub P natural log T2 over T1. That's how that's going to break out. Now, there's some caveats here. If and only if phase is constant. Why is that? Well, I'm plugging in because I'm saying du is equal to C sub P dt. So I'm plugging this in here and I'm integrating it. So when I do my integral, I'm pulling this out as a constant. If the phase changes, this is not constant, and this no longer represents the integral of this guy. This only works if the phase is constant, meaning liquid, well, I'm going to write it down here. This means you have to have liquid staying liquid or solid staying solid. Would not use this ever for R134. In our textbook, we don't have, well, we do have specific heats for liquid R134, but there's just no reason to. And it's all, I won't say it's impossible. It's very rare we would deal with a refrigerant that stays liquid, and we're not going to deal with refrigerants that go to the solid phase. You could possibly deal with solid water, ice. It's very rare. You'll deal with liquid water sometimes, but a lot of times, a lot of the problems we're working with, even if you have liquid water, it's probably going to a different phase. It's probably changing. Um, but if you do know you have liquid water staying liquid water, then this works. This is okay. What happens is um, when the phase changes, the specific heat changes. And so what you could do is you could find the entropy change for the temperature necessary to get the liquid down to the freezing point, and then you can find the entropy change necessary to get the liquid then cooling down in the solid phase, and then you would have to figure out how much entropy changes to actually cause the phase change. So you'd have to break it up into three pieces. But you don't have to do that if it's just liquid staying a liquid or solid staying a solid. You just apply this specific heat based on the fact is it liquid or solid in the substance. If you have a variable temperature scale, just pick the average temperature and go forward. Okay. All right, that's where I'm going to stop these. This is going to be the end of lecture 18. We'll pick up lecture 19 and 20, or lecture 19 and 20 is going to be mostly just example problems.